Hello. We are going to do a presentation about our work in Integrate project. So I'm starting to share my screen. So we're going to we are trying to build a user-friendly model to simulate different scenarios in integrated multi-traffic aquaculture in earthen ponds. So our names, I'm Sofia Gamito and Gabriela is near me. We are going to present the model. We work at the University of Algarve. First, I would like to say something about modeling and what is a model. Why do we need models? With the model, we try to simplify the real system. We try to do a description of the real system in order to understand or make predictions of the system. Some models can be a physical model of some process or a wave, the effect of a wave in a coastal system, for instance, or it can be a set of numerical equations to describe the system, and in that case, we use computers to run the models. Why do we need them? We need by several reasons to help to understand the complex system, and we are working in complex systems because we are working at the ecosystem level. So we are working at the limit. We can be working with hundreds or thousands of species, and the interaction between them and the effects of the abiotic factors in that species and all the function of the ecosystem. So it's quite a very complex system. So we have usually a set of observations, and from that we abstract and we simplify it. Of course, we need to simplify it. As I told you, the ecosystems are very complex. And from that simplification and from the abstraction, we try to convert the processes in mathematical equations and build the model in order to simulate and different scenarios and be able to predict and to test hypotheses, for instance. And from that conclusions and predictions, we can arrive to a conclusion that perhaps we need to do some more observations or a detailed experiment on some process to include that in the model. So this is a never-ending process. At the moment, we are building the user-friendly model in an integrated multi-traffic aquaculture, but it will work also in a monoculture in coastal earthen ponds. So we are using information from the observations gathered in Apple. So it's an experimental station in Olhão, near Faro. But also from the literature. And we are working with different species, fish species, such as the gilthead, the white sea bream, the sea bass, the mich, and the mullets. And also we are working, including in IMTA system, so it's integrated traffic aquaculture, also oysters. And later we will include the sea cucumbers and sea urchins. And we have also the macroalgae, for instance, the sea lettuce. As I told you, the models are always a simplified version of the real world. And the IMTA, or the integrated multi-traffic aquaculture, has the advantage that it can be considered as an ecosystem, but a simplified version of an ecosystem, where we have different traffic levels. We can have carnivorous or omnivorous fish and suspended filter feeding invertebrates, detritivores such as cucumbers, and also the natural occurring invertebrate species such as polychaetes and some gastropods and crustaceans, and the primary producers, of course, because it's an earthen pond with all the traffic levels. So we have the phytoplankton and the macroalgae, and it's not written here, but of course we have the zooplankton, and we also have the detritus accumulation in the ponds, in the bottom mainly. We have already developed a food web model using other software. It's not a dynamic one, it's an average of what we think it happens during a year in an earthen pond, and we can see that the ponds or the IMTA, it's a much simplified version of the trophic web that can be seen in the coastal lagoon nearby, and we can compare. And also the biomass is concentrated in the produced species, in this case the migrant, the bream, and the mullets, and also the oysters. While in the naturalized earthen pond, it's concentrated mainly in the natural occurring macroinvertebrates. So the aims of our model is to build a dynamic model to simulate the biomass variation of a production cycle that can be 1 or 2 years of the species that are being produced, and to create a user-friendly interface for producers and stakeholders. So at the end, we hope that the users will be able to simulate different production scenarios. We are using a software that allows us to build that interface. That is a Stellar Architect software. It works in different layers, and in the middle layer, we can build a conceptual diagram with the stocks and the flows and the rates, growth rates or whatever, included in that conceptual diagram. And then we introduce the algebraic equations and the graphical and the logical functions. And in the upper layer, we built a user-friendly interface that can be used by someone that doesn't know anything about modeling. They don't need to know what the equations, that they are equations, in fact, in the model, mathematical equations, and what the meaning of that equations. So they only need to know how to work with this user-friendly interface. So the basic structure of the model, in fact, is built with this conceptual diagram, and where we introduce the stocks. The stocks can be our fish, and we have an inflow that can be a growth rate that will increase that stock, so the fish we are producing. And we have outflow that can be, in this case of the fish, can be the natural mortality or the produced fish at the end of the production season. So our stocks or state variables are these different species of fish that I already told, the oysters, sea cucumbers, and so on, and the macroalgae. And I didn't put here, but of course, since it is an earthen pond, we need, and it is an ecosystem, in fact, we need to include also the phytoplankton. And the phytoplankton is important for the oysters, because the oysters are filtrating the water and returning the phytoplankton. So we need to introduce that state variable, as well as perhaps also the zooplankton, and the detritus will be also important to include. We have some forcing functions. The temperature is important for the organic, for the organisms that we are producing. They grow faster with higher temperatures. Also, the feed that we are adding to the pond, the pond management, the water renewal, for instance, the aeration to increase the amount of oxygen, dissolved oxygen in the water, and the species interactions. So the user interface will allow the user to select the type of cultures, if it is a mono, poly, or IMTA integrated multi-trophic aquaculture. We had some information such as the area of the pond. The user need to add this information: the area of the pond, the number of fish, and the average age, the number of production days, and so on. You will see later the small presentation about the model, the version we have now working on. And we are preparing the results. In fact, it will be simulation scenarios that the user can see, where he can see the total biomass produced, the expected biomass produced of each species, the revenue or the income, rough estimates, and also the effect of including another species in integrated multi-trophic agriculture. So now we are doing a presentation of the model. It's still in a rudimentary phase.
So here we have the model, the place there where we put the information about the model, the equations, the numbers of the fishes and the other species. So let's present the interface. The idea of the model is to have an introduction about the project and how it works, and the person can start and to choose the type of culture, monoculture, polyculture, or IMTA, the fish that the people are producing. And here we put the inputs of the values of the cultivation that are in cultivation. For example, the information about the farm. I will reset here and start again. And so monoculture, sea bass and sea green.
No, it's a monoculture, so you can select.
So yes. I'll put here polyculture. And 2 species. And so the size of the ponds in meters. And depth, it is important. And so the model calculates the area and the water volume and the data from the species. Here the period of cultivation, for example, 2 years in days. The initial weight of the fish, 50 grams. The numbers of the fish, 2,000, for example. And here we have the calculation of the density, the initial density and biomass. And so run the simulation. And it is a output example and with a graph of biomass, total biomass in tons by hectare. And here the final density, final biomass, and total production. So.
And you can see also the sea bream.
Yes.
No, doesn't show.
Let's see what happened.
You didn't put the information about the sea bream.
So it is not have all the information here. I will put the same. So now his output is here of the 2 fishes, the 2 species of fish.
Okay.
So, and here we can see the places on where the information is and some other graphs that we have already. So is that.
Okay, so this is our model for the moment. In fact, we have some more working hard in the model, and we are including also the income and because it's not very difficult to estimate, to include the income, so the knowing the price of the fish. Yes, you have here the revenue. This is one example. It's not in the user interface, but you can see that we can estimate only the revenue by selling the fish that are being produced, what is expected to get. Of course, it's not included here the costs with all the pumps and the aeration systems and the feed and all the costs of that. It's not included in the model. Okay, so that is what we wanted to show. I'm going to stop the sharing the screen, and that is what we have done for the moment.